Welcome back everyone, and in today's video we're going to explore something much different than we usually do. So on the screen right now I have the map of Zelda, and as you know I want to make an open source version of this kind of game with an open expanse. And one of the things I love about, one of the mechanics I really love about the game is the map, how the map looks and how the map functions. It uses something called, like the way it visualizes the map, it's something called topographics. It's a typographic display of how land masses, it kind of shows you the elevations of mountains. So you can kind of like have layers and layers of how high a mountain is. Like the darker the color, the lower it is, the higher, the whiter it is, the higher the mountain is, or part of the mountain is. And and the way the map works in Zelda is that you're allowed to add little markers throughout the game. So it actually is very good at where you place the markers, pretty much where it is in your 3D space. So we're going to try to implement something like this. We're going to we're going to turn our 3D terrain into 2D topographic map tiles. And, it works out really well. And and I found an example of terrain contour lines, a pixel shader. This guy, 90, gave a final version of it, and I managed to simplify it down a little bit and improve it a little bit for our case. But overall, it allows us to create grids on 3D terrain. So we can start looking at some source code right now. So let's go back to our HTML page. In the HTML page, we're going to bring in our test map shader. Everything is kind of the same. Ignore some of my comments. And we're going to use our old terrain object that we had from a previous video. And we're going to have, here's our specs. We're going to make it 4 units big. We're going to have it divided by 10 cells. It's going to have a minimum height of 0, and it's going to have a maximum height of 7 units. And here's the frequency and the seed. So we're just going to display one terrain. Okay. And our fragment shader, oh no, I'm sorry, our vertex shader is very simple. There's not much to it. And here we have our fragment shader. So we have some constants that we're going to have set up. Maximum y is the maximum height. Like a lot of these, most of these can be uniforms that you pass in, but right now they're kind of just constants. So remember I said maximum height 7, so we need 7 because we need to normalize a certain value. Grid size is how much to divide the world. So we're going to divide it by 0.2, and our grid world is divided by 0.2 anyway, the way we have the grid on the ground. How thick the line is. By keeping the line width a minimum of 1 or higher, we can actually simplify the original source code. We can get rid of the my. There's a couple things in here we can get rid of. We have the MA and the MI stuff values we can get rid of. And I did try out this code, and if I do a value that's less than 1, it doesn't make the line thinner. All it does is it makes the line more dim. So instead of having a black line, they just becomes grayer and grayer. So the smaller the number becomes, the closer to the white it becomes. So it for our case, I'd rather keep it as black and have at least a smooth black thin line of 1 pixel. So we're gonna change up the original fragment shader by changing some of the code, so everything has to be at min 1 or higher. So our lines have to be at least 1 pixel thick. We can't do like sub-pixel thickness. All right. So the first order of business in our fragment shader is we're going to take our our position, because we in our fragment shader or vertex shader we pass in our position as a variant. And so we're going to pass the position of every vertex into a fragment shader. So this way, when it does interpolation, every pixel that we render, we know the world position that pixel exists in. So we have the world position of the pixel. We're going to divide it by the grid size. So we want to know what is the grid size of the where in the grid does this pixel currently exist in, right? and then we're going to get fract. So let's say, we're bringing in like 0.7, right? And we're dividing it by 0.2. Like let's say the pixel at 0.7 height, it should return us 3.5. Typing wrong. So that should be basically our grid position, to be 3.5. And when we're dealing with a topographic, is that we just want to draw a line at the level, where every level begins. So we really need is just the fraction of where we currently are in the level. We don't necessarily need the level that we're on. Just in our current level, where are we basically? So it's kind of, we're going to do like a normalization type of thing. And that's what we're going to use fract for. We're just going to grab the fraction value. So we know we were at 0.5. So we know we're at the middle of our layer when we're drawing the specific pixel. So if I have these 3 lines of code in here, and this one has a return, so it exits right here. And here's what our terrain now looks like. All right, so we're basically kind of creating a mask. We're trying to figure out where in the grid are we. So wherever the black begins is really the layer. It's an easy division of 0.2, and when it comes to white is we're near the end. So like for that example, like we're drawing like a pixel around here, or really at whatever layer 3 is, like maybe around here. So that's the first thing that we divide our terrain into levels or layers. Now we need to kind of clean up the gradient, because we can't smooth one side is smooth, the other side is rough. So we need to smooth out each line so what we're going to do is we're going to shift the black. We've done this before, and we're going to do this again even in other videos. We're going to shift the black by half. So where this one creates maybe a range between 0 and 1, this one is going to convert the range to minus 0.5 to 0.5. Okay, so we're going to change the range of how we color. So what we end up getting just by using by just changing it, by minusing fact, we're going to get a lot more black and less white. So we're changing the gradient. And the reason why we're getting more black is because a lot of it now exists in the negative position. So at where the line now begins, it's now -5 instead of 0. So now we're going to do one last thing, and we're going to make an absolute value. So now the layers aren't going to be perfect at 0.2, because now we're going to make the line happen right at the middle of the layer. Because we're going to by changing the absolute value, we're going to change all this black that's in the negative zone. We're going to convert it into positive. So it's going to be, if it's a -1, it's going to become +1. So it's going to be going in the direction of white instead of black. So this hard line is going to go away, and we're going to start drawing these lines actually in the center of our grid. So we're going to be off by half. But for visualization, it's okay. It works out just fine. So if I click save, you'll see that it now shifts. Now we have nice lines, nice smooth lines that we can then work further to tighten up the lines. Now, the next part is we're going to get the derivative of the grid position. F-width is a function that uses the derivative of x and the derivative of y. And in all honesty, I'm not very good at derivatives, other than the fact I know that they are the rate of change. But you use F-width to help calculate the math. One of the things you can use is determine how to normalize something, or not normalize, but let's say we want to draw a line, and it's going to be we wanted to make sure it's 1 pixel thick. F-width allows us to, with a little formula, always calculate 1 pixel width if we wanted to, or 2 pixels or whatever. We can set a size, and no matter how zoomed in or how zoomed out we are, that line that we're drawing will always be 1 pixel or 2 pixels thick, whatever size we set it to. So that is the one of the uses of f width. Like I said, it's a formulation of 2 derivatives. If you want to read up further about it, but like I said, I'm not good at derivatives at all. Like, I fail calculus, so and I don't know how to use them very well, other than I know that they are just the rate of change. Like, we've used derivatives before in when we're doing Bezier curves. So we use a derivative to know the direction of change at each point during the Bezier curve. So just keep that in mind. That's what we're having. It's a derivative. If you don't understand how it works, I'm sorry. I can't explain it because I'm not good at it either. I just know that we can use it to do it. And this is the original formula the guy created. A lot of this determines on creating a line width less than 1. But if we get rid of that limitation and or add a limitation that our line width has to be 1 or greater, we can get rid of all this and just do this. And on top of that, if we want to, like, let's say if we're going to force a width level of just 1, we can actually simplify this equation further. Because if line width is 1 and we subtract by 1, that creates 0. And if 0 multiplies by the grid derivative, we're going to get 0. So it's going to be a minus 0. So ideally, or technically, since we have it set as 1, we can simplify this way. So let me just show you how it looks like. So we're going to basically calculate how thick how thick the line is going to be, and we want to make sure that we're going from the center and only 1 pixel. So we're going to turn this white gradient into a black line, essentially. And then after we're done calculating its grid size, in colors, we just multiply each axis with each other. Let's see, and that becomes our mix color. So we have the first color would be close to black, which is we're going to draw the line, and this is the second color, which is going to draw the actual background color. So we're going to make that's what C becomes. It becomes that mixed color, becomes a nice normalized value that allows us, like I said, to turn this gradient into a nice thin line. So I click refresh, and then we get our grid. So all those gradients become these lines. And we create, and like I said, since line equals 0, we can simplify the equation to this. Click refresh, and voila, it stays the same. It doesn't change, because like I said, if we're using pixel of 1, but that will fall apart if I were to change the line width. So if I undo it, and let's say I want to make it 2 pixels, refresh, now the lines are like that thick. And no matter how far we go, it looks thicker because the lines are getting closer and closer together, but the thickness of the line doesn't change no matter how far we zoom. And that's all because of f width and then this equation. So let's go back to line 1. Now, this works pretty well. It allows us to create a grid. Now, if we want to, for example, let's see what it looks like just without the coloring first, before I go a step any further, so you can get an idea what the values look like visually. Oh, okay. So it just creates a mask. So in the end, it just creates a mask, and this basically it just combines each axis. So by multiplying, we can create all the points that intersect. Like this point intersects on all 3 axes. So this is Z, this is Y, and then these lines over here this is X, that's Z, and these lines that kind of just flow out of nowhere, that is the Y position if we create a grid. So in all honesty, if you wanted to, you can just get rid of the Y, and you get a perfect grid that's on the terrain. So like if you're looking for an effect like this, just a grid on your terrain just for testing or something, this also works really well. You know, and it you have a grid that's 0.2, and you can change the size if you want. If you want to change it to like 0.4, you can make the grid bigger, and the maps out really well. Now, like the same thing that what I just did was by taking out the Y. If I take out X and Z, I will now get just the Y position. And now that creates the perfect topology grid that we're looking for that's based on Zelda. The only difference is we need to have the camera set up just right to render it, and without projection. We need to change our projection matrix too on top of that. So we're going to go through that too. So we're kind of the way there. So we already have our terrain, and like I said, we can color it very easily by using the C. Is basically our mask, because like the whole process was basically to create this mask, and we just apply colors to it. So now we have our colors and our lines, nice and smooth, very nice. Now here's one issue though. If you haven't noticed, we've done all this math based on vector 3s. So if I'm doing this division, I'm doing division 3 times because it's a vector 3. I'm doing for all 3 axes. Same thing when it comes to fraction, absolute, F-width. Everything is done in all 3 dimensions, and all we're going to get is the Y. That is actually a waste of processing time. So we can just rewrite the whole thing and just do all the math only in the Y-axis. Only in the Y-axis. And the equations are practically the same. So you have a V position and grid size. I'm just using Y. Saving it to Y, and then do all the math only in Y. We have a couple extra things. I do fraction Y, and then have fraction YA with an absolute value. You got to do some additional shifting. The shifting is for absolute value. No, it's done the same. So everything. Now, the only new function, the new variable we have is grid layer. It's like this one determines what layer we're currently on. It's basically the whole number. Remember that example I said we're doing 0.7, and we want to divide it by our grid size of 0.2, which gives us a value of 3.5, and fract gives us 3.5. In this little equation, normally you can just use floor, but since I'm doing shifting, I have to do a little bit of shifting first. So what I need to do is basically, you don't have to most of the time, but because of how because remember, when we create the gradient, we start drawing the line in the middle of the layer instead of at the bottom of the layer, so we can get a nice smooth line out of it. And since we're actually shifting the line to the center of the layer instead of at the bottom, we have to shift everything along with it too. So for me to get this value just right, I have to do a shifting. So I got to shift along. Everything has to be shifted together. So you got that, which gives us 3.0. And then you get a floor value, which takes out any fraction whatsoever. And then divided by 7. Layer count at the very top is how many layers we have. So it's maximum divided by grid size. It tells me how many layers we're going to have. So what this is telling, what I'm doing here is I'm trying to determine what layer we're currently in, or what level we're currently in relation to the total amount of layers that we can render, basically, for our mountains. This gives us a normalized value because we're using the big number in the denominator. So this basically gives a nice normalized value of where we currently are in our grid. So normalize the layer number based on total layers possible. Let's see if I click save and click refresh. We have the same thing, and the only difference now is that we are using the actual colors that we have hard-coded. All right, so the colors that we're using is a nice simple gradient that goes straight up. Actually, no, not really. Sorry. We are using a gradient, but we're using the grid layer value to know where currently we are as the mix value. So we're going to the line color is going to change the higher we get. So every layer gets a new color, and it's all done based on this normalized value of grid layer. So we mix the color for the line, and we mix the color for the height. So we have a low color, which would be for the actual layer, and then we have a low color for the line. So this way they look better. Because let's say if I do low, and let's click refresh, the top lines are a lot darker. So I want them to lighten up a little bit. So click refresh again. So everything kind of stays close to a similar shade. So it's not like a constant one color on the line. So the line color changes along with every level, and every level is one solid color because we're normalizing it by using that floor number. Now the only thing that left that we need to do that is that the existing topology, typographic things, maps, is that you notice that in certain elevations the lines are thicker. So I try to implement that too. So I try to determine the odd layer, like how many layers before I consider it an odd layer. So I say every fourth layer is an odd layer, and that every fourth one I'm going to make the line thicker. So here's the odd layer. So it's just math. I'm just flooring the grid again. I'm just getting the solid number, and then just doing a mod of it. And modulus. So if you know what modulus does, it gives you between the 0 and the number you are modulating -1. Usually, if you're dealing with whole numbers. So if the layer equals 0, then I know, or if the odd layer equals 0, I know it is an odd layer. So there you go. So that's 0, 1, 2, 3, 4, because I say every fourth. So that's 0, 1, 2, 3, 4. So as you can see, we can determine every odd layer that we want to highlight. So the next thing, since we know at what point we want to make the lines a little thicker, now we need to be able to change that layer. So we say width line width, and if it equals 0, and if the fraction is less than 0.5, we're going to add 0.9 to the line width to make it a little thicker. Why am I doing this? Is because the reason why I need to do this, I'll probably just show it to you. Why not? So every time we hit that odd level, we're going to make the line thicker. So if I click refresh, I need to change C. Same equation, just different order of operations. Whoa, refresh again. Now, here's the thing you might notice. Here's the fourth layer, and it's highlighting both because it considers both lines as part of layer 3. So that is the reason why I said, well, and fract y equals less than 5. So I want to just color the lower end and not the upper end. So just by adding that little and in there, I will only highlight the bottom line of the layer and not the top. And there you go. So you have the thicker line here, and then you got 1, 2, 3, 4, another thick line, 1, 2, 3, 4, another thick line. So now we're developing a topology, not topology, topographic value very similar to the Zelda. And that's pretty much it for the rendering. So we basically turned our 3D mesh, and we're rendering it for topographic type of viewing. And we got the colors, we got the lines, and we got the thickness changing based on elevation. So now we have to figure out how we're going to render this. Now, so the first thing we're going to do is we need to set a size. So I want to say my tiles are going to be by 512 by 512. So here's our tile. So this is our image tile. So it's our canvas. So I made the canvas smaller, very simple. Now the next thing is that I'm going to say goodbye to this camera, and we're going to do a few things. We're going to use orthographic projection, and we've used it before once to do an isometric view. Now, orthographic projection allows you to do 3D, but without perspective. So everything doesn't look like it's like folding in on itself, and everything becomes kind of flat looking. Let's see if I do this. And the ortho projection allows you to define what the borders are, or it helps you define what is the dimensions, or I don't know how to describe it. It's a way to convert your 3D world space into 2D view space. So you can define what the maximum values are. So in our case, we're defining the values 1 for the right. So the right side is going to have a maximum value of 1. The left is going to have a maximum value of -1. Top is going to have 1 and -1. So that essentially makes the center of our grid, or center of our canvas, 0. So it's kind of like your typical viewport, because that's a viewport actually is defined by this. So this is really how it looks. So I'm just going to create a projection using those values, the near and far. So the near is -10 and the far is 100. And all we do is just saving the information into our main camera, and we're just getting the inverted projection matrix. So we don't need to do this for this thing, for this video, but the inverted is used for raycasting. So that's why I just do it. And then once we have our projection all set up for our camera, we got to pass it into our UBO. So this way our shader can then use it. And I'm also saving the width and height of our screen. Some effects need that. So this is our hard to see. I don't even know where our landmass is at this point. Okay. But we need to set up the camera. So we need to set up the camera to be at the center of our canvas, but rotated by -90 degrees. So this is where we're looking down on our world. So if I click refresh, there you go. So that's why I couldn't see the terrain. It's too high. Okay. So like I said, this is -1. That's 1. That's 1 here, -1. And there's our center. Works perfectly, right? But the problem is our tile, our image starts way over there. And like I said, this allows us to define our dimensions, that how we translate the values. And don't forget this. Our size of our chunk is 4 units big, so I can define our dimensions are for orthographic view this way. So I'm going to say the left is 0, the right is 5, top is 0, and 5 is not 5. So the reason why I'm making left and top 0 is that I'm going to change the center point, which is with using these coordinates as a center. I'm going to shift this all the way to that corner. So this corner will become 0, 0, 0. So to go down, you have to go into negative. To go left, you go positive. So if I click save, refresh. So now we can see our tile. Now it's you might be saying, well, it's not perfect. Well, it's sure it's not perfect because I use the values of 5. So it's 5 units. Our texture is 4 units. So I just wanted to show you that we're shifting our entire viewport to that corner. So that is now officially the new origin. So the last thing we have to do really is just match up the resolutions. So 4, 4 for right and for bottom, and refresh, and there you go. Our tile is now perfectly fit into our 512 by 512 canvas, and we can just say save image as. That's it. And now you have a map tile. Now, ideally, this is not the best way to go about it and as a web application because you have to set up every single tile. You have to right click and save. This works better if you're going to do it in like an application where you can feed in all your terrain chunks and then have it render out each one. You can do something like this with a web application. You just have to be a little more creative. So, like for a web application, you can sit there, have a loop that renders every single tile, but then it has to upload the tile to some server. Like you can set up like a local server and just do like a file upload and save the tile on your hard drive that way if you're going to use a web application. So you can still do this as a web application where you can render the entire terrain, like all your terrain as individual map tiles, and then use them in your game to actually create a world map like Zelda. Probably hopefully it looks better because my terrain is very simple looking. And they will they're seamless. That you can connect the next tile together, and I've done it in testing. So this is how you can basically approach into creating maps out of your terrain. You don't have to build your terrain in chunks either. You can have one big massive terrain and just change the position of your terrain, like set the position and just increment your position based on how much you want to increment their tiles. So you can have the entire scene, like your entire world created, and just output them tile at a time. And you can, in using orthographic view and having the camera set up to look right on top, like I said, it makes your tiles perfect. You can use these tiles to help make a mini map or a world map like Zelda. And since, like an example here, this tile is a 1-for-1 to the 3D terrain. So if I were, let's say we're going to use UV coordinates. Let's say this is the top corner, this is the bottom corner. If my world X and Z position is like here, I can normalize it and then use that normalization value to determine which position in this tile that you're currently in. So this way, your terrain chunk and your tile for your terrain chunk is 1-to-1, and you can very easily map your current position in 3D space to a 2D map or to a mini map as well. So this is so this is really a big solution of how to build maps that you can then use to add markers to or to easily locate where you are in the world. There you go. It's like a real GPS mapping, basically. You can build very simple GPS mapping because now you can correlate your 3D world position to a 2D map. So, yeah, there you go, and that's it. And that's really all. Like I said, it worked out. I can save all the tiles out. I'd save like 2 or 3 tiles. I'm able to put them together into one long mesh. Click save, refresh, and let's go back to our 3D world. There's our terrain. Oh, I forgot to put the camera. So we're kind of done. I just wanted to show you one last thing just for funs and giggles. I was going to say the S word, but I'll get flagged for that. So I just have all the other terrains. Click refresh. And there you go. So I have other tiles or other chunks of other chunks. And I have them all placed out, and they're all the exact same size. They're just positioned everywhere. And, you know, you can, like I said, you can then turn around and turn your 3D world, your 3D terrains into tiles. And if you want, you can also use this shader as just as a test shader. So you know you can have your character exist here, and you can kind of see just the overall elevation of your world as like a test texture if you really wanted to. You know, which kind of divides the world by elevation, and you can make the thick lines by certain heights. You can say, you know, if you want, there's some very certain reason why you want certain values. I don't know. Like I said, it's up to you how you build your world. But I just wanted to show you that you can, you know, this shader can be used for a lot of things. If you like, just overall, just you want to see the look of it, or that you want to build a topographic 3D world, or like maybe you're making a map tool. Maybe this will help better if you're doing, you know, not doing gaming. This is like more for geology or something. So, like I said, I really couldn't find anything. I found bits and pieces like that, how to do the contours, but never found a shader that actually did this completely. So I'm really happy I managed to work this out on my own and have it ready for you guys to kind of use. And like I said, my inspiration was Zelda because I really loved how their map system works. And if I ever build my game, I want to have a similar map system because it looks really cool. And I always wondered how to build a map system, and I finally figured it out. And then I managed to actually do it on my own. So it's kind of neat without using no one's tutorials on how to build a map. That might be it might be a big issue because I didn't look at anyone's tutorials how to build maps. There might actually be better ways to do this. So just take what my approach is as one possibility. There might be better ways to go about it, but like I said, this is one way you go about it. You just turn all your 3D into 2D tiles, and just by changing how you render your landscape. You can render your landscape any way you want it, and you can create your tiles any way you want to. Like I said, you can keep your real textures, and just render it that way. It's fine if that's what you want your map to look like. If you want something a little more cartoony, a topographic view of your terrain might be better. Like I said, this is more cartoony. There's more of a toon shading thing going on. That's why I was kind of cutting everything in layers, because that's kind of like ramping for toon shading. So yeah, I think that should be it for this video. I probably rambled on too much at the end. I hope you learned something. I hope you had fun. This is something very different, but it could be a big deal for anyone building a game and that you really want to do a map system. And you need to be able to do a 2D visual representation of your 3D world and be able to correlate your actual position to the 2D map. So that's it. Please like and subscribe, and thanks for watching.